Okay, please write me in the chat box whatever you want to say, and you can just stop me at any time.
Okay. Thank you.
Okay, now it is recorded, right? Recording is started,
Yes.
right?
Yes. Yes.
Okay. So, what do you mean by petrophysics? This is a very vast topic. Petrophysics, petra means rock and physics means nature. It is the study of physics and chemical rock properties and their interactions with fluid. Petrophysicists are employed as reservoir engineers or geoscientists. Then they are employed to help the reservoir engineers and geoscientists. So this study is very important to understand the rock properties of the reservoirs. It may be water reservoir, it may be hydrocarbon reservoir, it may be geothermal reservoirs. Okay, so it may be oil, gas, coal, or it may be geothermal reservoirs. It may be the storehouse, store reservoir of the carbon sequestration. Particularly how the pores in the subsurface are interconnected and how it is controlling the accumulation and migration of fluids or gases inside the reservoir. These things are very important to know for exploration of energy from that particular reservoir. So under the subsurface and at the subsurface, what is the rock property? Is it a real reservoir? Is it actually the good reservoir, or it is not effective for the hydrocarbon exploration, or it is not effective for geothermal exploration? If it is effective, then what kind of technology you need to implement for that kind of reservoir? So for that, you should know the properties, and those properties are the petrophysical properties. So you can imagine how the petrophysics are important for energy exploration. So there are several methods of petrophysical property analysis. First one is coring and spatial core analysis, seismic interpretation or seismic sections, seismic studies, then well logging. So here especially we will discuss about the well logging techniques and little bit about of spatial core analysis also we will discuss. And we will not cover much about seismic, because within 1 hour, these three are actually three different courses. So it is not possible to cover all the techniques in detail. So we will focus on well log as the detailed technique for evaluating the petrophysical properties for energy exploration. So core analysis or spatial core analysis, seismic sections and well logging, this can help you to understand what is the porosity, what is the depth, what are the permeabilities, density, resistivity, and all the conductivity properties, then all the properties of rock we can understand using these techniques. Cores are mainly drilled from the wells, and they are analyzed using several techniques. You can do routine core analysis and spatial core analysis. For the conventional reservoirs, we do routine core analysis, which include the normal petrophysical property studies, megascopic studies. Using the normal microscope, we can understand how the sediment textures are behaving. Then what is the grain size? What is the grain size and how it is varying from area to area? All these things we can understand from the normal core megascopic analysis as well as petrographic analysis. Then for the spatial core analysis, we can go for high resolution scanning technologies like microcomputer tomography, then scanning electron microscope, which can give you the high resolution image of the rocks. So you can we can see the 1 millimeter at nanomillimeter scale, what is the variation of the grains in the rocks that you can observe using the spatial core analysis techniques, which includes scanning electron microscopy, microcomputer tomography, then some mineral analysis technologies like XRD, FTIR, then XRF for chemical properties of rock analysis. Those are also carried out for core analysis. And using those properties, here you can see, first one is the image is showing the cores. The second one, this image is the original image taken from the core using the high resolution scanning electron microscopy. Then you can process the image and you can visualize the 3D form. What kind of internal structure is present under the core? with a naked eye or with some conventional microscopy, you cannot observe what is the texture at nanoscale. But using higher resolution scanning electron microscopy, you can observe the nanopores, how the pores are connected. The pores are connected or they are isolated. If the pores are connected, then permeability will be high and it will be very good for reservoir, because reservoir means the storehouse where the hydrocarbon can store as well as it can flow easily. So it should have the permeability. So that these properties we can understand using the spatial core analysis. And these properties you can calibrate with well logs. So we will discuss what is well log. Well log means graphical representation of the subsurface petrophysical properties. For petrophysics, how it is used for oil and gas reservoir exploration, that we will discuss now. We will discuss about the common well logs like gamma ray log, caliper log, SP log, resistivity log, neutron density log, and borehole image log. These are the logs. So log means these are the graphical representation of petrophysical properties of rock under the subsurface with respect to depth. So at what depth, what is the petrophysical property, how it is varying from top to bottom in the well, that you can find out from these logs. And petrophysical property means the conventional petrophysical properties are lithology, porosity, water saturation, permeability, thickness. Then some of petrophysicists use acoustic and density measurement of rock to compute the mechanical property and strength. They measure the compressional P wave velocity, sound through rock, and the shear wave velocity also. Okay, so these measurements are useful to design the program to drill the wells that produce oil and gas. These measurements are also used to design dams, roads, foundations of buildings, and many other large construction projects. They can also be used to help interpret seismic signals from Earth. The seismic signals may be man-made or it may be due to earthquake. So gamma ray log, caliper, SP, resistivity, neutron density, borehole image log, these are the common well logs, and we will discuss these logs one by one. Here you can see one track and there is one drill well. So under the subsurface, there are so many rock layers, and at different depth level, what will be the petrophysical properties that we can understand from the well logs. A standard well logs include gamma, then SP log, resistivity log, then density, neutron log, porosity log. So well logging is a continuous record of measurement made in borehole. It measures variation in some physical properties of rocks through which the borehole is drilled. So these are the graphical representation of petrophysical properties. Here the logging unit, this includes the logging service. So there are several logging service companies in different countries. Each unit has some common components like logging cable, then rings to raise and lower the cable to the well. Okay, then self-contained vault AC generators, then surface control panels, then downhole tools, sons, okay, and digital recording system in the truck. They will record the signals, and that record will be processed, and after processing you will get some logs, some graphical representation, and that can be interpreted for the petrophysical properties. So what are the petrophysical properties? These are gamma, SP, okay, logs, these are the logs. And what petrophysical property we can calculate or we can determine using gamma? Here red color is showing the direct measurement, okay, and the green color is showing indirect information what we can get from these logs. So gamma will directly measure the mineralogy or lithology. SP, you can get information about lithology. Then sonic log, it will give you information about porosity and indirect information about the lithology. Density, it will give direct information about porosity. Then neutron, porosity, nuclear magnetic resonance, that will give you information about porosity, and indirectly it will give you information about lithology. Then fluid type, fluid saturation, permeability, stratigraphic information, all of information you can get from these logs. And the core analysis, that can be calibrated with the log analysis, because from the core you can get all this information at laboratory scale. Now, what is the principle of gamma? So gamma has the component of a gamma spectrometer. Then it is depend on the depth of investigation. It has some vertical representation. So let me tell about the gamma principle. It is actually the gamma ray, and it is the penetration of electromagnetic radiation arising from radioactive decay of atomic nuclei. And the gamma ray can be produced by atomic nuclei through decay of naturally occurring radioactive elements. What are the radioactive elements? The radioactive elements are thorium, uranium, and potassium. So the decay of lab-produced radioactive elements and bombardment of atomic nuclei at high energy subatomic particles, and they can generate some gamma ray, and for different petrophysical properties there will be gamma ray variation. As I have told you, that this is depend on the concentration of uranium, potassium, and thorium. Okay, so wherever the uranium, potassium, and thorium concentration will be high, it will show the high value in gamma. Here the scale is 0 to 150 degree. So whenever it will enter into the shale formation, or the gamma high value, then it will show the gamma high value. So the concentration of this uranium, potassium, and thorium will be high for shale. Then concentration will be low for sandstone. Then concentration of gamma will be very, very high for organic rich shale. Then it will be less for limestone, dolomite, and it will be again high for shale. So whenever you will enter, the gamma ray will show a low value, then it represents the sandstone. Okay, it may represent sandstone. You have to calibrate other logs also along with gamma ray log. And whenever you will find high value in gamma, it may be organic shale, or if it is very, very high, then it may be organic rich shales. From gamma, you can calculate the shale content also. Why it is important? Because for conventional reservoir, you have to identify the reservoir rock, which is having less shale and which is clean sand. Okay, so how much shale volume is there within the clean sand, that you have to calculate, and you have to deduct that volume for reserve estimation. For this is the equation where you need gamma ray log value, then gamma minimum, gamma maximum, then gamma minimum value to calculate how much shale volume is there inside the along with the sandstone. Then natural gamma ray spectroscopy tool has been used as advanced gamma ray log because the gamma ray log give you the total concentration of uranium, thorium, and potassium. But it is coming due to uranium, or it is coming due to thorium separately, it does not give you the value. So this one, natural gamma ray spectrometry, is the tool which will give you separate value. So you can understand from the NGS log that the high gamma is coming for organic matter, or it is coming for presence of some uranium in the shale, or it is coming due to potassium or thorium separately, if it gives the values. Here you can see left side, this log is normal gamma, and the right side it is giving it is the spectral gamma. Here you can see separate concentration of the uranium, thorium, and potassium. This is one example of black shale radioactivity. A spectral gamma ray log over the upper Jurassic black shales of North Sea is showing that this high gamma is coming due to the presence of uranium. Gamma ray also can help you for sedimentary phases interpretation. different shape of gamma. These are indication of different environment. So cylindrical, it represents uniform deposition. Bell shape indicates finding upward sequence. So where you can get finding upward sequence, it may be some tidal shans, braided channels, fluvial channels. Then if it is funnel shape, that indicates that portioning upward sequence, generally in deltas. Then distributary mouth bars, barrier bars, traverses plate. These depositional system shows some portioning upward sequence. So based on the signatures or orientation of gamma ray log, you can find out what is the depositional system of that particular depth. Another log is caliper log. This log helps you to measure the borehole shape and volume, environmental correction, then quantitative interpretation of cement volume calculation. There are different types of caliper log. It may be 3 arms, 4 arms, then multi-finger caliper log. And these caliper logs are used to measure the borehole diameter. So if the original, what is the difference between original diameter and a borehole, and what difference you are getting due to mud crack deposition or due to some fractures? So that information you can get from caliper log. So these are the equations how you can calculate the mud crack. If the diameter of caliper diameter is less than bit diameter, then you can see this is the equation how to calculate the mud crack. So shale may indicate borehole enlargement. Spiky curve may indicate fractures. Here you can see what are the variations of caliper log for different formations. For brittle shale, you can get caving. Then slugging shale, you can get slugging. Impermeable limestone, there is uniformity. Permeable sandstone, there may be mudcake deposition if the sandstone is highly permeable. For marl, you can get such type of deposition. And for shale, it depends. If it is rich in clay content, then there may be mudcake deposition. So this is very important to understand the borehole environment based on the caliper log. Another important log is spontaneous potential log, that is called SP log. It measures the electrical potential in the formation caused by salinity difference between the drilling mud and the formation fluid. So when you drill a well, you have to insert the drilling mud, and there may be already existing formation fluid. Okay, so formation fluid may be water, it may be oil, or it may be gas. And drilling mud, it may be oil-based mud or it may be water-based mud. And nowadays there are a lot of chemical additives, nanoparticles we are using with the drilling mud. So our main aim is to understand what kind of formation fluid is inside the reservoir. Then how much hydrocarbon is inside the reservoir. For that, it helps to delineate the permeable zones from the impermeable zone. So here you can determine the formation water resistivity. If the mud filtered salinity is less than formation water salinity, okay, then SP will show you the negative value. Then shale, it has low it will show low SP, and tin sandstone, it will show high SP. In case of when the mud filtered salinity will be greater than formation water salinity. Okay, mud filtered means drilling fluid salinity will be greater than formation water salinity. Then SP value will show you the positive signatures. So high SP will indicate shale and low SP will indicate sandstone. And when there will be no difference between mud filtered salinity and formation water salinity, then there will be no SP. You can see the straight line. So generally, for a shale, you can see a straight line, a very uniform line, and we can consider it as shale baseline. And based on that, we can understand what are the other lithology. So SP and gamma help you to understand the lithology. You can differentiate sandstone, shale, limestone using SP and gamma ray log. Then another log is resistivity. Resistivity, this log is used to understand what is the resistivity of any formation. So these are electrical well logs that record the resistivity of a formation. Resistivity is usually recorded in ohm meters and it is displayed on the fourth track of the, or it may be displayed in the second track of the well log. So resistivity logs are logged in three depths, I mean lateral depths: shallow, medium, and deep. So based on this, as we have time limitations, so we cannot discuss elaborately about resistivity log. Simply, you should know that the resistivity log will give you information about the fluid. What kind of fluid is present inside the reservoir? Here in this graph, the green color is showing these are the sandstone. The low gamma is showing the sandstone. You have three sandstone layers here. And you can see the resistivity log is very high for that particular sandstone, 1 and 2. But the bottom sandstone, that is showing very low resistivity. Almost it is showing, you can see it is the log scale and it is showing almost 20 resistivity. But resistivity is very high for these two zones. So these two zones are the hydrocarbon bearing zone. So whenever you will get high resistive zone, that indicates that it has hydrocarbon. So seismic is also important to understand the petrophysical properties, and you should know about the depth information and some reflection data. Well logs can be used as control point for seismic reflection data, and the well logs can be used to predict with the along with the seismic response, which will help you to improve accuracy in data interpretation. Then another log is neutron log. Here you can see for different formations, you have different neutron values and neutron porosity. So wherever you have a reservoir log, it should have good amount of porosity also. High neutron value indicates good reservoir and low neutron value indicates less porosity. And this neutron log is displayed along with density log. Here you can see neutron and density log. For shale, it shows low neutron because shales, the pores are very small. They are in nanometer scale, so it is very difficult to resolve. Resolution is not much in these logs to understand accurately how much porosity is there in shale. For that, you need spatial pore analysis. For sandstone, it shows greater value. Neutron log shows greater value when it is porous sandstone. For tight sandstone, it will show low value, less value. Then density. Density is very important. You can identify coal very easily with the help of density log. Here also you can see coal is here, and for coal it has very, very less density. It is almost 1.2 to 1.5 gram per cc. Okay. So coal has very, very low density. If it is there in your area, if there is coal under the subsurface, from density log, you can identify it very easily. If there is hydrocarbon, then also it shows less density. For tight reservoir and shale, you will get high density value. Here the image 3 indicates integrated logs, gamma, resistivity, then neutron porosity and density. Here gamma shows less value for the sandstones. For that particular sandstone, here 1, 2, 3 sandstone layers, and for 1 and 2 it has high resistivity. Then the third one, it has very low resistivity. It indicates there is water, no hydrocarbon. Then if you have identified that your reservoir is filled with hydrocarbon, then how much hydrocarbon is inside that? That is also important to know. And what kind of hydrocarbon? It is oil or gas. How will you know it? You will know it based on the density and neutron log. When the density will be very, very less, then it indicates that there is gas. For oil, the density will be comparatively high than the natural gas. So there will be separation between density and neutron log. If the separation is very high, it indicates it is gas. So that is called gas effect. This is just one example how to display the logs. You can see here how to display gamma ray log, resistivity, and using the softwares you can find out what kind of lithology is there, and manually also you can find out from the logs. So this is how you can differentiate oil bearing, gas bearing, and water bearing zone. You can directly from the resistivity log, you can differentiate the water bearing zone. Then from the density and porosity log, you can find out if the density porosity separation is high, then it is gas bearing. If the separation is low, then it is oil bearing. So that was all about conventional logs. You can use these well logs for unconventional reservoirs. What are the unconventional reservoirs? Like shale gas, tight gas, shale oil. Okay, so here this is one example from for unconventional reservoir. Here the well logs are used to understand how much potassium, thorium, and uranium is present there. Then these are the equations. These are some equations. You can take screenshot of these equations because these equations are helpful to identify how much organic matter is there in the shales. For conventional reservoir, we do analysis for sandstone or limestone, which are the reservoir rocks. But for unconventional reservoir, as shale act as the reservoir rock, so we do analysis about the shale rock. Okay, so how much shale is present there? You can how much organic matter is present inside the shale, that you can calculate using this equation. Although core analysis is important to analyze the organic matter in the shales, but if you do not have core data for the whole well, whole field, if you have only the exploratory well in that field, so how will you calculate the core data if you do not have the source of core samples? Then how will you calculate the core data? So if you have at least one well in the field, or if you have at least one exploratory well in the field from where you have collected the cores, so you can calibrate the core data using the equations from the well logs. So well logs can be used to calibrate the data, or you can extrapolate the data using this equation, and you can map the TOC content for the whole area. So I hope you have understood that core data coring is very expensive. So you may not have core samples for the whole field. Okay, generally you may have one or two exploratory wells where you have taken the cores from any particular area. But how will you get information about the another wells or another regions? For that constraint or for the restrictions, you can calibrate your core data with the well log data. So whatever I have given the equations, that equation you can use to map the total organic content. And here you can see this is one example of Eagle Ford shale, where we are using the equation 1 to extrapolate the total organic content. This is the map of TOC. The second map, this is the average bulk density of the Lower Eagle Ford. And the third map, this is total organic content of Lower Eagle Ford, and which is determined using the equation 2 in the previous slide, what I have shown you. Sorry, I'll go to the previous slide. So here you can see these are the equations. First equation, second equation, third equation, these are used to, first equation is based on resistivity. Here you need resistivity baseline, then density data, and 2.5 into density minus the row baseline. So you can extract this information from well logs. This third equation is based resistivity and based on sonic. Then the fourth equation is based on only the delta log R that you can get from resistivity. So for detail of these equations, you can read Pesci. There is one paper, Pesci, a Smoker, another paper, and you can get here also Yao Tionet 2013. They have also done a lot of work on these equations, and they mapped the area based on these equations. So you need only one well core data information. That data can be extrapolated for the whole field. Now the image, this is formation image log. Okay, this image log can it can give information about the fracture orientations, then conductivity and resistivity of the formation. And this image log is very important to analyze the fractured basement or fractured reservoirs as well as for unconventional reservoirs. As for coal-bed methane also, for coal also this is important because microfractures play a very important role in unconventional reservoirs, because unconventional reservoirs are tight and it does not have high permeability. So microfractures need to be stimulated with the help of hydrofracturing, so to extract the hydrocarbon from the reservoir. So in that case, what is the orientation of the natural fractures and how they are creating the networks and how to connect those networks to the drilling well? It is very important and we need this information for that. Then photoelectric factor, this is also one log which can be used for lithology interpretation. It is almost like density log. And it is also displayed with density log for shale, light, and hydride, gypsum, what other variations in this log that you can find out here. This red color is showing the photoelectric factor log. And you can see for anhydrite, it is high. And you can see what are the variations for different lithology for photoelectric factor. Then this is one case study from Cambay Basin. This is situated at the western part of India in Gujarat. This basin is one of the rift basin in India, and tectonic plays very important role in the petroliferous basin, character of this basin. And there are several highs and lows in this basin due to upliftment and downthrow at different geological edges. And mainly here, the Eocene Cambay shale is the source rock. Above that, it has Kalol formation. This is the reservoir rock. And the specific significance of this basin is that this is commercially producing basin for conventional oil and gas. And now it is considered as one of the prospective basin for unconventional oil shale oil and shale gas basin. So this basin is very important in India. And this is one case study and example from this Cambay basin. Here, left side first log, you can see this is gamma. Then resistivity in the second step. Then in the third step, you have here C and F, that is the neutron porosity, and ZDEN, that is the density log. Red color is indicating density log. Can you see here very, very low density in that zone? And this zone is indicating that there is coal. In the lithology of this depth, there is coal. Above that, there are a lot of shales, and you can see the sandstone layers are marked with yellow color. For you can see for red color, this is the sandstone which is having high resistivity. It has low density and high porosity. So this zone is considered as hydrocarbon reservoir. These are different data. I'm showing you how to do petrophysical interpretation. You have to find out for the specific depth. You have to find out gamma, SP, RT, neutron density values, and for that you have to do the interpretation. What kind of fluid is present there? After that, porosity, then neutron porosity value you have to find out, and you have to calculate the water saturation. Then these informations are important for estimating how much hydrocarbon is present inside the reservoir. So how to calculate? You have to use you can use manual interpretation, or you can use softwares. But manual understanding or manual interpretation is very much important for accuracy of your result. So conventional versus unconventional petrophysical model. Conventional reservoirs are different from unconventional reservoir, because in case of conventional reservoir, you have matrix. Matrix consists of effective porosity, where you may have the pore space are maybe filled with water, oil, or gas, and that is called the reservoir. Effective porosity zone of that reservoir is called a reservoir. But unconventional reservoir includes 4 porosity component. It includes the effective porosity part, as well as total organic matter, clay porosity, and free shale porosity also. So here these parameters are quite high, and if porosity is low, in other part, effective porosity part, you will get high porosity. This is highly porous zone, but other part, it is comparatively less porous or tight zone. So it is very important to understand the effective porosity, as well as total organic carbon related porosity, clay porosity, and free shale porosity in case of unconventional reservoirs. So here, unconventional reservoir includes matrix as well as fluid. Matrix include kerosene, then inorganic matrix part, where there are a lot of mineral components. Then fluid include gas, or it may be water. This is one example from Woodford Shale for shale shale gas reservoir, typical shale gas reservoir example, which is showing very high gamma for the hydrocarbon bearing shales, organic matter rich shales. As I have earlier informed you that whenever the gamma ray will enter a highly organic matter rich shale, then it will show very, very high value. So here you can see very high value. Resistivity is showing high value. Then density, it will show low value comparatively. Okay, and photoelectric will show low value, because it is related to density. So already I have discussed the PESIS method. So you can take screenshot of this also, and you can refer PESIS method for detail about these things. And or you can sometime, if you need the elaboration, then I will discuss on, because only this estimation of TOC from logs, it takes a lot of time to explain actually. So if you are interested, then sometime I can explain you these informations. So how these methods can help you to understand how much TOC content is present there. This is also another example. Here you can see here this black color. This is the total organic matter content, which is collected from, or which is laboratory derived using spatial core analysis. Okay, laboratory derived TOC analysis. And the log here, the red color is showing the log, which is the TOC derived from the equations. So you can see sometime it may vary. Sometimes the equations will not follow. There may be not accuracy. So for particular field, you should have at least 4 data from one well. Then geomechanical properties also we can analyze using the well logs. We can analyze Young's modulus, then brittleness. These are the examples from different shales, Niobrara shales, then Woodford shales and Cambe shales. For different shales, you can see how these things are helping in to identify the brittle zone. As in case of shale gas exploration, brittleness is very important, because you have to fracture the zone. If it is very tight and ductile, then or due to clay-rich region, it is very difficult to go for fracturing or artificial fracturing. So you have to identify the sweet spots. Sweet spots mean brittle zone with rich in organic content, where there is high amount of shale gas. So brittleness identification is very important in case of shale gas reservoirs, and using the Young modulus versus Poisson's ratio, you can analyze the brittleness. Nowadays, all of you may maybe heard about how the whole world is moving towards the clean energy and climate change. These are the hot topics now, and trending topic for research also. So we are also moving towards the CO2 sequestration. CO2 can be sequestrated, it can be stored and sequestration. We can do sequestration in saline aquifer. We can sequestrate in the depleted reservoir. So geophysical informations, at what depth you can sequestrate, at what depth there is hydrocarbon bearing reservoir, and what depth there is the depleted reservoir, where is the porous reservoir, that we can get information about the geophysical data. And already you know that what information, porosity, permeability, water saturation, and everything we can get information from the well logs. Then laboratory tests will also give you information about porosity, permeability, and water salinity. What is the water chemistry? This is also important for CO2 sequestration. And then from that, all the data, you can simulate this data to create the geomechanical earth model as well as reservoir models. And you can do the simulation using the software, and that model can be utilized for the field scale implementation. So geophysical, laboratory, and petrophysical informations for petrophysical property evaluation for a particular area is very much important for CO2 geosequestration. It may be sequestration at limestone cave, or it may be sequestration at marine condition, deep sea, or it may be sequestration in saline aquifer, or it may be sequestration in depleted reservoir. For all these, you need petrophysical informations. Without knowing about the reservoir, you cannot do CO2 sequestration, or simulation you cannot do. Then another application of petrophysics is geothermal exploration. This is also one of the energy resource. This is renewable energy resource. This will never going to end. Okay, geothermal means the heat generated from the earth core. There are many places where the geothermal gradient is very high at shallow depth. And there are some examples where there are hot springs. Okay, so the hot springs can be used and utilized for the energy resource for heating purpose. And those hot springs or heat can be utilized for any household purpose, or it may be utilized in industries also. So geothermal energy, these are the one of the important resource for mankind, and it is never going to end till the earth, the mankind is here, because this is renewable energy. And in this case, well logs play a very important role in identifying the geothermal prospect in a zone. Here, this is one example from North German Basin. And here, this basin is one of the major type localities for deep geothermal energy. 3D seismic sections were carried out for this area. And two research well were drilled here. Here, you can see in this research well, borehole gamma has a smooth signal for there are some salt rock, smooth signal, and it has transitioned to anhydrite. And for geothermal, if you have geothermal reservoirs, then for resistivity log, it shows very less resistivity and high conductivity. Geothermal regions are very highly conductive zone actually. So from the resistivity and gamma, you can find out from its lithology as well as if there is geothermal gradient, that what is a geothermal gradient, you can identify that. So here in this example, it is a zone which is having, and this basin, from the well, it is considered, it is find out that it has deep geothermal, not at shallow depth, it has deep geothermal. Okay, but in some area, it is exposed on the surface also. You can observe some hot springs. USA, it is very common. USA, Nevada area. It is, high, from the shallow depth also, they are exploring geothermal energy. So this is integrated interpretation of magnetotelluric gravity, then drill hole and historical data. This is one example from Newberry Volcano, Oregon. And here, if it is high fluid flow in the geothermal area, then you need porosity and fluid saturation data. Then if that, in that case, you can go for magnetotelluric tool. If it is high temperature zone, then you can go for magnetotelluric plus gravity. And if it is at higher depth, like the earlier example, if geothermal reservoir is at higher depth, then you have to go for seismic reflection. In that case, magnetotelluric and gravity will not act. So here you can see the low resistivity zone, red color. These are the zones which are having, these are the prospective zone for geothermal exploration. So integrating all this data, you can identify where you have the geothermal prospect. Here also this section is showing the resistivity variation and the low resistivity, the red zones, these are the zones which is having geothermal reservoirs. So with this, I would like to conclude this because we have some time limitation also. As you came to know that petrophysics, this is very important, aspect. It has very important role in energy exploration. It can help you to establishment of interesting zones which show presence of hydrocarbon. It can help you for estimation of hydrocarbon reserves. Then CO2 geosequestration also, you should know the reservoir parameters. And if you want to evaluate the reservoir parameter, at what depth you can go for sequestration and what kind of reservoir is there, you should know about the petrophysical properties. And at stage of the presentation, I already explained how the petrophysical properties can help you for geothermal energy exploration. So all the there are several techniques for petrophysical property evaluation, including routine core technique, spatial core technique, then well-logs interpretation.
It's 9 o'clock.
Geophysical interpretation, including seismic, gravity methods. All these are important. And for research purpose, I just explain you these things within 1 hour. But all these terms has all these topics. It includes wide study. So you can do study on CO2 geosequestration. You can do study on geothermal exploration using petrophysical properties. So you have n number of areas here. You can work on methodology or technology development or design development for energy exploration. So there are a lot of research scope for this, petrophysical field, and there are a lot of career prospect also in a petrophysical field. So I believe you like this presentation, and if you have any question, you can ask me. So now this is open for question and answer. If you have any question, you can ask me.
Thank you so much for the presentation, Dr. Anna.
Thank you so much, everyone.
We have a few questions in the chat box.
Yeah, sure.
Adekule Feromi asks if well-logged data can complement magnetic data. Did you get that?
Just wait. I'm checking it. Okay.
Adekule Feromi, he asked if well-logged data can complement magnetic data.
Okay. Can well-log complement magnetic data? Yes, of course. Actually, one single data set cannot give you accurate information. If you want more accuracy, then you need to integrate all kind of data. Okay, so magnetic data, if you are talking about magnetic survey or geomagnetic survey, geophysical technique, as in case of geothermal energy, I explained that for different kind of fluid, for different kind of depth level, you need different kind of technique. If your reservoir is at higher depth, then you have to go for seismic and well logging. If you want to know few basic information about the subsurface for up to shallow depth, then you can go for magnetic data.
Okay, thank you so much.
Yeah, so please kindly help me with some likely data to work for my master project. Yeah, sure. I would like to have, it will be my pleasure to help you. You can contact me. I'm sharing here my email ID. Okay, you can contact me, and you can contact me in my LinkedIn also. Okay, so I hope you got my email ID. Okay, so I cannot see any question. I hope you liked this lecture. So whenever you will have any query, you can get back to me. And if you can switch on your camera, I would like to take one picture. If the participants can switch on your camera.
Thank you. Please, can you turn on your video? We want to take a snapshot.
Okay.
Doing that.
Okay. So thank you so much. Thank you so much.
Thank you very much.
Thank you for joining. And I would like to thank Society of Petroleum, Society of Exploration Geophysicist, then Federal University of Technology, Ekua, Nigeria, and faculty advisor Emidio, then Rodiet. Thank you so much for inviting me. And I would like to thank all the participants. We have participants from UPES also, I can see. Yeah, thank you, all the participants. Thank you, and see you again.
Thank you very much.
And my apology for you to changing the time. It was scheduled for your morning, but due to some reason, I had to reschedule it. Sorry, an apology for the same.
It's fine. Thank you so much. We really appreciate you.
Thank you.
Bye.
Bye bye.
You can end the meeting.
Good night from India.
Bye. Good night. Good day. Yeah, see you in the afternoon.
Evening. Yeah.
All right.
Thank you.